In the next section, we look at resizable arrays. That sounds like a contradiction in itself because arrays tend to have a fixed size. But there's a trick to make them feel to the outside world as if they could be resized. And it's a very standard trick, so I want to show this. If you want, you can say an array is both a data structure and an abstract data type. Let me say why I think that is. Both can be justified. We can say an array is something that you can create with a fixed size. And yeah, Java can do this like this. In Python, you can create a list of a certain size, but it's not a real array. It is a resizable array, actually, beneath the hood. Every list in Python is a resizable array. But in Java, we have real arrays where the size is fixed and you cannot change it after you created it. And that's what I want to understand when I say array, it's fixed size. And Python lists are lists. We can get the ith element in the array so that we can access an element by index. And we can override the position by index. And both Java and Python use the square brackets to do that. And the important thing is fixed size. As I said, at construction time, you allocate a fixed chunk of memory, and that is it. We can also say an array is a data structure because it actually says, by fixing these operations, well, by the term array, we usually think of a concrete representation in memory, namely a contiguous piece of memory where we put the elements one after the other. There's a starting pointer, and then you can just add offsets to get to the other positions. So array is the one thing where I'm not sure if we would better call it an abstract data type or a data structure, because it has features of both, and it's so fundamental that it might be a bit outside of this distinction. A fun metaphor I've heard is arrays are a bit like the sharks of evolution. They've been here forever. They're still very efficient sometimes, but they're also a bit limited. So let's treat them as a data structure because they're built into most programming systems. And their implementation is usually fixed to this contiguous chunk of memory. Now, we started this section calling it resizable arrays. So that doesn't work normally. But we can have at least something like arrays based on, we can have stacks based on arrays without a fixed upper limit on the size. And the idea is we change the array once in a while. When it becomes too small, we create a bigger one and copy everything over. And we do this. So one way to do this is to say, I currently have n elements in the stack. I want that my array that I'm maintaining, in which the stack is stored, has a capacity of, well, at least n, because I have to store all the elements, but also never more than 4 times the number of elements. Okay? In other words, the number of elements currently stored in the stack is between a quarter the capacity and the full capacity. If we can maintain that, we can always add more elements because we always have a capacity a bit left, maybe after re-establishing the invariant. The rest of the implementation remains unchanged. We keep an array and we keep an index of the topmost element. Now, how do we make this magic happen that we always have the capacity like this? And the simple answer is, before you push a new element on the stack, that's the point where you might run out of space. If we do run out of space, if we have filled the stack to capacity, then we double the size of the array. Okay? And then you take a new array of twice the size. You take all the elements from the old array and copy them over. And likewise, if we pop an element, we might violate this other end of the invariant. We might have that the array is now too empty, in which case, again, we create a new array of size 2n. But in this case, this actually shrinks the capacity of the array in half, or roughly around that. Because if we violate this bound, then our n is roughly a quarter of the current capacity. So if we go to twice that current size, it's half the current capacity. Okay? So two simple rules. And that's what people mean if they say resizable arrays. Maybe with slight twists if you actually double or change that 2 to some other factor. Other than that, that's what's behind resizable arrays. Question?
Can you explain the after pop?
The after pop? Well, if you pop an element, it might be that the stack is too empty for us to allow it. We don't want to have more than 3/4 of the array empty. And if that's the case, we halve the capacity. What's written on the slide is a more sophisticated way of saying that, but it comes down to the same thing. If your array is too empty, you make an array that's half the size, and then it's no longer too empty. Okay?
For example, if we have 1,000,001 elements, I mean, we have 1,000,000 elements, and we try up one more element, and we double 2,000,000, for example.
Yeah. Okay. So the comment is that this seems to be expensive, right? So it can be expensive in different ways. It can be wasting space. So you might be inclined to use a smaller constant than 2 if you want to not have as much spare capacity. It also is expensive in time because if you have to resize, you have to copy all those elements over. Both are legitimate concerns. But still, this is very widely used. So are people all just misguided and use something that's not really efficient? Let's have a quick check if you understand this invariant. There you go. Did I set this up as multiple choice? You can tick several answers? What a mean bastard. Okay, 5, 4, 3, 2, 1, and locked. This is an interesting one because all the answers got roughly, well, a quarter of the votes, right? Only one is really correct, but this was a mean one. Let me briefly explain why. After we've analyzed it. So from what I've said so far, you can eliminate some of these. The first one can't be really true because n is changing all the time. If I add another element, that would mean if I say exactly an array of size 2n, that would mean whenever I add a new element or remove an element, I have to change the size of the array. But that was not what we were doing. We said we only allocate a new array in these extreme cases when the capacity was completely used up or when it reached a quarter. Okay. For the other things, bear with me for a second. There's a second reason why I'm discussing this resizable array primitive data structure, because I want to do a little bit of amortized analysis with you. And this might be something not everyone has seen formally. So maybe time to wake up for the computer science graduates. So we've already discussed briefly that sometimes these push and pop operations are insanely expensive because you have to copy a very large array to a new array. So in theta terms, it's linear time effort to copy all these elements. And we have to do this at the push and pop. There's no discussion. The trick here, why it's still a fairly good data structure in many applications, is if you have such an expensive operation, suppose we only add to the stack. After you've just done such an expensive operation, you have twice the capacity that you had before. So you have to wait a long time before you have to double again. And similarly, if you popped elements off and you reach this low threshold so that you made the array half the size, you're definitely still so you're then at roughly half usage of the memory. So you need to pop quite a few more elements before you have to do the copying step again. So we can offset, we can amortize the expensive operations against the many cheap ones that they must entail. And so this is waving our hands, and the intuition behind this is it looks like maybe on average the operations are cheap, but let's try to be a bit more precise and quantitative about this. And that's what people call amortized analysis. This might look a tiny tad scary, but we'll go through this in a slower pace. What we'll do here formally is we define a potential. That is a number assigned to a current state of the world. And our world is the array. This potential is traditionally called phi, and so I kept that. And here what we want is phi should somehow express how far are we away from an expensive operation. Now, the catch here is expensive can mean if I have many pops or many pushes. I can go up and down, and so we somehow have to reflect the distance to both of the expensive operations. And one way to do is to define a potential like this. We have the current size of the array n and the current capacity c. And we take the smaller of these two distances. What this means is, maybe use more space. This is our array S, which has capacity C. And it's filled up to some point n. That's occupied by our, well, that's currently filled with elements in our stack. And now there's 2 points where things happen. At a quarter C and at C. And so our potential measures the distance to these 2 interesting points and takes the smaller of the 2. That's what the potential intuitively does. And you can work out using the invariant that we maintain that it is always, it's never negative and it's never more than 0.6 n. That's just if you insert the boundary cases and look where this is maximized. Okay. Okay, so the question is about what happens if you create a list in Python of a certain size. So in principle, all lists in CPython, in the standard reference implementation of Python, are resizable arrays. I'm not sure if they use a factor 2 for doubling or if they have a different trade-off. you can have a look at the code. It's open source, and they might have other special cases. If you create a list from another list where you know the size, maybe the default is to create then an array of exactly that size as opposed to the next power of 2 or something like this. These are details that I don't know from the top of my head how they're done. But something along these lines happens. If you keep appending a new element to a list in Python, you will have this doubling or this resizing once in a while. And you can measure this and somehow prove indirectly that Python uses this, even if you're not looking at the code. Okay, so we have this potential. It's a definition. You can take it just as that, but you can also think about it that it measures how far are we away from the dangerous cases where we have to pay. And now we define what's called the amortized cost of an operation, which is not the real cost, but something like every operation pays a little contribution towards the next expensive operation. That's the idea. So every operation has an actual cost, and here we count the number of array accesses as our dominant operation. And it's corrected by this term that only makes sense after you've completed the analysis, really, why there's this -4. But there is a correction term that contributes the potential. So if an operation decreases the potential, which means it brings you closer to the edge of paying, then the amortized cost goes up. Okay? And if an operation brings you further away from the dangerous cases, then the potential increases, and so the amortized cost decreases because you're paying for that up front. What we have to do for this, maybe before we go into these steps, let's have a look at what we get at the very end. If we have a sequence of m operations in total, then we can bound the total cost that we actually pay for that sequence of operations by the total amortized cost that we will analyze in a second, plus the final potential, the final number of credits. And we'll see that this works out to theta of m plus n, which means it's linear in the number of operations and the size of the final array. And okay, yeah, you need both. The array could be very small at the end, or it could be roughly a size m. Before we continue with this, I want to show you why this inequality is true. And for that, I'll denote by AI the amortized cost of the ith operation. So A is for amortized. And it has an actual cost, that's CI, C for cost. And we subtract this, go away, 4 times the change in potential, okay? So we need a notation for this phi at a certain point in time. So I'll write phi I to say this is the potential after the ith iteration, and phi I minus 1 is the potential before that operation. So that's just a way to assign names to these different parts so that we can work with them in the formula. What we'll show here is that this is at most 5 in all those cases. We'll go through that in a second. But what's behind amortized analysis in all cases is the following observation. If I sum up all the amortized costs, I on the one hand know that this is at most 5m, because each costs at most 5. But also I can rewrite this sum by inserting the definition, and then I can split the sum. So I get the sum of all the actual costs. That's what we're really interested in. We only care about actual cost, not amortized cost. The amortized cost is only a means for the analysis. And then we have this correction term. So we have a sum over all these potential differences. And if you look at this sum, this is a telescoping sum. Each term we have a phi I positive, but then if you go to the next I, where I is I plus 1, you subtract phi I again, because for I plus 1, I minus 1 is I again. And so these all cancel each other. The only thing that's left is the very first and last one. So we end up with the actual cost, the sum of the CI, and what's left is the last, and we subtract the first. And so we get an inequality like this. Need a bit more space. And so we can rearrange this. This is what we're really interested in. And now we have an inequality less or equal 5m. And we bring this to the other side. So plus 4 phi m minus 4 phi 0. And because our potential was never negative, we know that we can just drop this and it only gets bigger. And so this is what you see spelled out here. 5m and 4 times the final potential. Now, we don't really know what the final potential is actually, but we know the potential is never more than 0.6 n. So we use this upper bound there. That's how we get there. Now, the step that I skipped before was to show that the amortized cost of each operation is always at most 5. So that's what's explained here. And we have to distinguish the different cases now. If we have a cheap push or pop, that means it's one where we don't have to copy. We don't have to resize the array. So we can move with n one up or down, and c remains unchanged. So the actual cost is 1 because I have one array access. The potential can go up or down, but at most I have to consume 1 credit. And so the amortized cost is 5 because I have one actual cost, and I might pay minus 1 in the change of potential, times minus 4 becomes a plus 4. Okay? At most 5 if I have a cheap operation. It could be cheaper. It could actually have amortized cost minus 3. But we only need an upper bound. What happens if we push and have to resize? The actual cost is 2n plus 1 because I have to create an array of the new size, and then I have to read n elements, write n elements for the copy, and one more element because I'm pushing a new one. That's 2n plus 1. If you do the math, it happens to come out that you create 1/2 n credits. And for that, you have to look at what the situation is here. So your array is currently entirely full because it's an expensive push. That means n was the capacity before. And so you resize the array so that it now has twice that capacity, and the new n is here. Just this one more element is used now. So the distance to this boundary that matters is the one here to the 1/4. And so you see that this is roughly 1/2 n. And you can work out, if you count exactly, you get to the 1/2 n plus 1 credits that you gain. And if you multiply that by 4 and add the two things up, then you see that the 2n that you pay for the copying and the 4 times the credits you gain, they just cancel each other. And magically, it sums to 5 again. Okay? And similarly for pop, the situation is quite similar to the other one. You get the same picture at the end, but you start with a bigger array where only a quarter is filled, but then you resize the array to be only half that big. And so again, it's the distance to this point that determines the potential, and that's again roughly 1/2 n. And previously, you had the potential at 0. So now you're again at 1/2 n new credits that you created by shrinking the array. And again, multiply this by 4, add the two things up, multiply by -4, comes out to 5. Okay? I know these proofs sometimes look a bit magic. The way it works is you think of a potential that intuitively makes sense, and then usually you have to play with the definition of amortized cost until it works out. If you want to see this in action, watch the video from last year where I had to do this on the fly because I messed up the first round. But now it works as it is on the slide, which has the benefit of being correct, but is not as instructive to watch. All right, let's finish this off. We already had the questions. I'm not asking it again now because we've discussed it at length. This is the right answer because that's the outcome of the amortized analysis. The total cost for M operations is linear in M, and it's linear in the size of the array, but either of which could be bigger. Why are the other answers not correct? We talked about the first one, but the second one is not always correct. Adding or deleting an element at the end only takes amortized constant time. If I do this many times, on average, every operation is constant time. But each individual one, if you say you look at this from a worst case perspective, might be linear time because it might be one of those expensive ones. The last one is almost the correct statement. It talks about the right type of time, constant amortized time, but deleting or inserting any element means also in the middle of the array, and that doesn't work because you would have to move elements over. So that was kind of a trick answer. All right, let's do the rest a little more quickly. Queue is another abstract data type, which is quite similar to a stack. You have only two operations. You can enqueue on one end and dequeue on the other. So it's like a queue where you wait. You add yourself at the end because you don't cheat. And you get popped from the front or dequeued from the front. And so it's first in, first out. You can do essentially the same implementations as for stacks based on a linked list or based on an array also for queues. Another slightly less, not as often used abstract data type is a bag, which tries to abstract what the two have in common. I just want to throw in this because it exists in the libraries of programming languages sometimes. A bag is something you can put something in and you can get any item out, but you're not, it's up to the implementation to decide which item is removed. You just get any. It's sometimes convenient to express as a programmer that what you are using here is a bag and you don't care in which order the items come out. That could be useful because then you tell the programming system, the compiler, that it can do optimizations that change the order. So that's why it's sometimes helpful to have this. It's a way of expressing your intent. You only need a bag. Now, you might use a stack underneath it just because a stack is a good implementation of a bag. But if you say you're actually using a bag, that means other options are possible. That's why it helps to separate abstract data type and implementation.